Hey class, Adam Ward here. I want to talk with you about how we can use our Solute tracer data to get at the advective terms in the system, otherwise known as getting at the modal velocity, or how fast our tracer is moving down the stream channel. So the first thing that we're going to try to do is find the advective timescale. So how long did it take? So here's our study reach with flow going from left to right. As always, we've got our injection with some small mixing length shown there in green, and we have upstream and downstream solute tracer time series at the green and purple x's respectively. So the data that we would expect to look at looks something like this if we plot concentration through time, where 0 being the time that we made our injection. We expect our two pulses to do something like this. Now, to estimate the advective time scale of the problem, we're simply looking at how much time elapsed as we went from the peak at the upstream to the peak at the downstream. So that is the advective time scale of the problem. And I often use T with a subscript ADV to abbreviate that. So TADV. Now, if you've got a constant rate injection rather than a pulse injection, that's no problem. What I've seen used in a constant rate injection is to take the same time elapsed, but for the steepest part of the rising limb. And so, for example, if our rising limb at the upstream end is shown in green and at the downstream end is shown in purple, what you would do is take the steepest part of that rising limb, and the time elapsed between those would be your advective time scale. Now, as we get to velocity, we need to also know not just the time scale, but the distance. So I've shown in yellow here what I'm calling delta x. So the time scale or the spatial scale, between the up and downstream points. And from there, we can calculate modal, and it says velocity back behind where my face is. Calculate modal velocity. And so what that means is, what is the most common velocity, or in other words, what's the velocity that the peak experiences? And we know that's distance per time, or in this case, delta x, the spatial scale, divided by TADV, the temporal scale. So from our solute tracer data, we are now able to estimate the advective time scale as well as the velocity.